Hello everyone. I'm going to present an overview, or most likely just bits and pieces, about climate change assessments and methods used by different researchers for this purpose. My familiarity with this topic comes from working on various projects dealing with studying the relationships between weather and weather-induced insurance losses and forecasting the effects of climate change. There are some of the research papers that we have published and provided our results, and there is also a review paper that put our work into a broader perspective of whether our methodologies are positioned in the global trend of integrating statistics and data science approaches. I also led a team of editors working on this book about quantitative evaluating of climate change impacts. The book consists of several chapters solicited from leading topical experts and presents their perspective on the assessment of climate change effects. It is astonishing how diverse the topics presented in this book, and they go well beyond insurance, where we experience the impacts of climate change. Today, my first part of the talk will be about insurance risks, so basically the left side of the screen, and then I will introduce some of the chapters which cover other topics beyond the insurance claims and insurance risks. So part 1, insurance risks, and here I particularly focus on home insurance. Some of the relevant works in this area are about 20 years old. Remembering that insurance industry is part of the financial sector because it deals with accumulation and redistribution of financial assets, I'd like to first mention this study by Grace and co-authors who used econometric models, and they concluded that price elasticity of demand for catastrophic coverage is higher than price elasticity for non-catastrophic coverage. They concluded that based on the data from the United States for 2 states, Florida and New York. Why it's so, and does it make sense? So for catastrophic losses are rare, right? And you may say, well, the research shows that people are not very good in estimating very low probabilities. In particular, we tend to overestimate low probabilities of positive outcome. That's why there are still so many people buying lottery tickets. But actually in this insurance example, it sort of makes sense. In fact, when we aggregate insurance data over a big territory, such as a big country, or looking globally as much as we can, we will notice that normal extreme weather, normal bad weather, cumulatively has led to more losses than catastrophes. Yes, it's fun to watch the news about hurricanes with all the thrill and minute-to-minute updates, but so-called low individual but high cumulative impact events still bring more cumulative losses to the insurers. And another thing to mention is that catastrophes are often covered by so-called reinsurance. Those are really big companies which insure the insurance companies. So they're like a second layer of insurance. Whereas low individual by high cumulative impact events are not covered. So the whole burden of these events lies on our local insurance companies who sell the insurance policies. The next study, PRESS, used a regression model to model financial outcome of several companies based on weather. And in this research, whether it's not specifically on damage of property, I put it here because the author specifically suggested to look at non-catastrophic weather. The next study by Fries and colleagues also used United States data, and They looked in more details on different perils and further classified non-catastrophic weather risks into separate groups. Based on the US homeowners data, they showed that wind and water damage are the most frequent perils, whereas hail damage has the highest median damage. From these three perils, water, wind, and hail, hail is probably the least predictable. Even with increasing quality of weather forecasts and climate projections, we still experience challenges with hail estimation. In turn, the models are usually better in forecasting precipitation and high winds. Here I cannot just skip the statistical part of this talk. When we have the data on insurance losses and related variables, we will be trying to model the risks, Y's, as a sum of some explained variability, mu, and unexplained variability, epsilon. We also often call this unexplained component the residuals. One simplest way to continue with this model is to model the risks as a linear combination of predictors, for example, weather variables. It could be precipitation, wind speed, it could be the precipitation in the previous day, precipitation in the previous week, etc. And coefficients beta that scale up the effects of these covariates on the risks. So this is the most simple model. However, this model has a number of limitations. One of them is that relationships are assumed to be linear, and another is that the residuals epsilon are assumed to be normally distributed. And insurance data are everything but normal. They show so-called heavy tails. So to model these non-normal distributions, we can apply a next class of model called generalized linear models. Here we generalize our distributions to a bigger class of distributions from not just normal, and we will apply specific transformations to transform the data. So technically here we will be modeling, for example, not the mean of, or not the expected value of the normal distribution, but we will be modeling the expected value from some heavy tail distribution such as negative binomial distribution. And we will still use the same explanatory variables such as precipitation, wind, etc. After applying the transformation, we still are limited by the assumption that the relationships are linear. The next step in the feast of statistical models is to relax this linearity assumption. So we will keep our transformations, but we will also allow at least some of the variables to be non-linearly related to the risks. And here the nonlinear transformations are denoted with some functions, f1, f2, f3. These are nonlinear functions. We don't necessarily know how they look like, but we can approximate them. A very popular method is to approximate them with simple smooth functions. So imagine if you have a simple function and you can fit this function locally and shift it many times and then add the results together. So you'll get an approximation to a more complex function, to a more complex relationship which you observe in the data. We can apply these approximations to individual variables, like here some x1 and x2 can be precipitation. We can also apply these transformations or functions to interactions of variables. For example, precipitation and temperature could play a combined effect. And we still may have variables which preserve just linear relationships with the data. Of course, we can go even more complex. Here we have been modeling the mean risk, for for example, mean losses, mean number of claims, but we can use separate equations for each parameter. So we can model the location parameter or the mean, also the scale, the variability, and also shape parameters of the distribution, and that it would be generalized additive model for location, scale, and shape. Many forecasts or projections that we deal with operate with these models, and imagine instead of the observed weather variables, which are represented by X as here, we will just plug in the projections from climate models. So this is the general framework for assessing what would be the outcomes or risk scenarios in the future. The climate models are estimated under different climate scenarios. Under these scenarios, we will have different forecasts of weather variables which can enter our statistical models. So where the data science methods come to life? We have statistical models, but we will likely also need some algorithms, and we will also likely need expertise from the data domains to tell us what we are doing. It means for me, I should be in love with data, I should know all the details of the data, and I should also collaborate with a researcher who is much more familiar with data than I am even. If we're talking about data science research in climate, means that we need a climatologist on the team, means that we will likely also need a programmer on the team who will help us to design and implement different algorithms. Algorithms help us to find solutions and implement our statistical models more efficiently. Here I have an example of two algorithms we applied to insurance data. Those were data from Norway. We looked at the relationships between number of claims and precipitation. We used two different methods at the border of machine learning and statistics, so I would say data science methods, to find thresholds. The method of classification and regression trees is a tree-based approach which takes all the data on precipitation and number of claims and tries to separate the insurance data, number of claims, based on the predictors. In this case, it automatically selected the threshold of 12 millimeters per day, and we have this decision tree saying that if the precipitation is below 12 millimeters per day, we will likely see 0 claims per day. Otherwise, we will see 0.6 claims per day. So this is a very simple decision, but it already tells us that there is something going on at about 12 millimeters per day. Possibly, if we are looking at predictions for the weather, we will be concerned when we see that the forecasts tell us that this will be a precipitation above 12 millimeters per day. When we applied a different method called alternating conditional expectations, this method looks for transformations of the variables that maximize correlations. If we look at precipitation and number of claims, how can we transform precipitation to maximize the correlation with number of claims? On these graphs, we see the observed precipitation on the horizontal axis and transformed precipitation on the vertical axis. I think the second plot is even better because it shows that basically when we are in the area of precipitation of 0 millimeters per day, 5, etc., 8, up to probably 9 millimeters per day, there is almost no effect on the number of claims. But after a certain threshold, marked here with a red star, we observe clear and increasing effect. So as the precipitation increases, the number of claims increases almost linearly. So both these methods use iterative processes to come up with the thresholds or come up with these nonlinear transformations. And they enhance our statistical models. How we can incorporate it into the models and how we can apply it to further estimate the change in the risks. We came up with several methods to use these thresholds we identified and then to plug it back into the statistical models to get those estimates. Because, for example, when we look at the distribution of precipitation, it looks approximately like this. We have a high frequency of very low precipitation days, and again the distribution is heavy tailed to the right. We have some days with heavy precipitation. Here dk is the threshold we identified, and of course we can just calculate the proportion here, but the proportion doesn't have the same unit of the variable that we used in the model. So we need to preserve the units. We need to have the same units as millimeters per day to plug it into the model. So we designed a couple of different approaches presented in these papers to basically numerically integrate the tails of the distributions. But it's a fancy name, but the idea is the following, is that we separate the tail of the observed and some forecasted distribution. For example, the distribution that comes from the climate model. We separate the tails into many small bins, then calculate the frequency within each bin, and then find the differences and also multiply them by actual centers of those bins. So in this case, since we will be using the centers of those bins, so they will be in the same units as millimeters per day or whatever variable you are using. So then we were able to plug back the estimates into the statistical models. It turns out that it's easier statistically to estimate number of claims than losses for various reasons. Again, losses are even more heavy-tailed than number of claims. Also, we don't always have information on the price of the house, on the insured amount, all those variables that determine the amount of loss. And there are several algorithms that help to approximate losses. One of them is presented here. It's a two-step algorithm. So first we estimate the number of insurance claims per day. These are data coming from 4 Canadian cities, and we see observed data marked with bars, and the fitted distributions are marked with curves. So we use this Sichel distribution, which is used for economic data with heavy tails, and we see that in some cases we have a good fit, like for CTC, we model the observed data very closely. In some cities we miss a little. Nevertheless, this fit is much better than if we would just model losses. Then we can use the tail comparison approaches to shift this distribution to the next 10 years, for example. Then we will know the distribution of number of claims, for example, in 2030 to 2040. And then we can use observed claim amounts to sample randomly and then to come up with the distribution for the claim amounts in the future. So by repeating these 4 steps, we were able to project the amounts into the future. How can we compare different methods when we are not sure which one is the best? Here again, data science methods are used, such as different cross-validation techniques. When we have a large enough data set, we can separate the data into different folds, and so-called validation fold will be left aside, whereas we will be training our model, so estimating all the coefficients and studying the relationships on the gray data, and then forecasting for the validation fold. And we will be able to assess the performance of the model, calculate errors, etc. Then we will repeat this for the next fold, etc. Every time the gray data will be used for training and the color data will be used for validation. As a result, we will have average performance over the data. There are other methods in cross-validation, also leave one out cross-validation, assuming that we are leaving only one observation out. There is also a validation technique where we separate the data into previous and future data, especially when we have strong trends and dependencies in the data. In general, we are trying to select cross-validation technique which is similar to our task for the model. If the model needs to forecast in the future, then likely we will design the cross-validation in such a way that we train on the past and then forecast on the future, and using the known data evaluate the performance. The data come in all stages of analysis, and data quality and quantity are very important. In one of the papers we ran a scenario of different data usages. The reason for running this analysis is that for the current data we can use observations from weather stations. For example, we used long-term observations from around airports, because those are usually weather stations which have the longest records. Or we can use model data. So when the climate models are evaluated, they have so-called evaluation runs in the recent past. So we can use the gridded data from climate models to feed our statistical models. Why it matters? Because for the future we have only model data. So it might be the case that it makes the difference whether we are comparing model with model or model with observations. In our analysis for 4 cities, we ran these 3 scenarios where we compared model with model, model with observations, and we saw that in general the conclusions agree that there will be a general increase, for example, for the number of claims in all cities, and actually the magnitude also is very similar across cities. However, the results not always agree that well. Some of the results we obtained are very different based on the different climate projection we are using, or based on different climate model. Models don't always agree, and sometimes we observe that the greatest difference comes from different models, not even from different scenarios of climate. So there lies a lot of uncertainty in the future risks as well, because uncertainty of the models propagates into the uncertainty of our statistical forecasts. As someone clever said, it's very difficult to make forecasts, especially about future. As the second part of the talk, I'd just like to introduce some of the other topics where we see the impacts of climate change. Of course, fires, the wildfires, and here the authors used extreme value distributions to model the fire weather index. Of course, the problem of high tide flooding. Here the researchers used regional ocean modeling, satellite data. They made projections for Annapolis, Baltimore, and presented their results, again dependent on different scenarios of climate change. Also, climate change impacts biodiversity. Here our researchers, Ryan Woodland and Jeremy Testa, used generalized additive models to model biodiversity indices and see how they change and might change again with the climate change. Climate also impacts other climate-sensitive industries, for example, electricity and, in general, energy sector, energy consumption. In this chapter, cost-benefit analysis is used to showcase what are the potential benefits we can get and how many times we can save if we implement certain adaptation measures. I participated myself in the chapter on studying the impacts of weather on traffic accidents. We didn't do forecasts far in the future, but we used a very good data set from Mexico City and studied the relationship using random forest techniques and, again, generalized additive models. And of course, the last topic that I kind of left out is the relationship of climate with agriculture. Agriculture risk management is very important, but it's also probably one of the oldest research topics. As long as the agriculture existed, there have been many different approaches applied. Risk assessment in agriculture often depends on our ability to forecast yields, and there have been many wonderful research papers trying to forecast yields. In this chapter, again from our book, the authors used integrated modeling and socioeconomic analysis, trying to bring all the information that we have access to about future climate, about different policies, about trade policies, to model the risks.